Okay, we ought to know this by now. We better. So how about Diana, what's the meaning of the input of sine? Yeah. Okay, Jared, agree with that? The input, right? The input. So say it again, Jared. Measure the angle, so counterclockwise from 3 o'clock. That's right. And what are all possible inputs? Jared S. What are all possible inputs that we could put for angles? Look at that for angles. Okay, so is that all possible? Anything we could put into sine? Can we put in any? That's right. Yeah. Yeah, because we could, right? We can have positive angles. Those are our counterclockwise angles. And after we get done with 2 pi, 1 rotation, we can just keep doing another rotation. And we can just keep going as much as we want. And then what about negative angles? What are those about? Going clockwise from 3 o'clock, right? So 1 rotation clockwise is negative 2 pi. And then we can just keep going. So there's no number, there's no real number that we can't say is an angle measure swept counterclockwise from 3 o'clock. All right, meaning of the output. Corey. Keep going. Yep. Measured in radius lengths, right? Vertical distance above the horizontal diameter and radius lengths. Okay, so it's vertical distance above the horizontal diameter. To what? To what? So for any angle, what we're measuring up to what? So we haven't. This has kind of been implied the whole time. We should probably talk about it. Okay, so we got some angle, right, like this. That's our input, right, our angle. And we're measuring the vertical distance above the horizontal diameter to where? To what? Yeah. Alex, what's that? Well, one radius length is the maximum it could be, but for any angle, so we're measuring vertical distance up to what?
The whiteboard.
Okay, of what?
Of the point of the intersection of the red on the circle.
The circle, right? So this has been implied all along. We get that terminal point is going to intersect the circle somewhere. That point on the circle is what we're talking about. So I'm going to add this detail in here that we've just kind of, it's been implied all along. The vertical distance above the horizontal diameter to the circle in radius lengths. And we'll see why I'm pointing that out, because we're going to have a new function that's going to be similar but different. So that's one of the differences. So with sine, it's this vertical distance above the horizontal diameter to the circle, where that terminal side intersects the circle, right? In radius lengths. Okay, what are all possible outputs, Brooke? -1 to 1. Right, so -1 radius length is the lowest we can get on a circle. And 1 radius length, the top of the circle, is the highest we can get. Okay, so we want to look at a new function here whose input is the same. So it's the same as sine, it's the same as cosine. It's the angle swept counterclockwise from the 3 o'clock position. Okay, but now the output, it's also going to be a vertical distance. Okay, it's also going to be a vertical distance, but now it's going to be a vertical distance along what we call the 3 o'clock tangent. So if we drew a tangent line, a vertical tangent line to the circle, it's the best circle I've drawn all day. Okay, so that blue line is what we're going to call the 3 o'clock tangent. Why? Because it's tangent to the circle at the 3 o'clock position, right? So now we're going to measure vertical distance above the horizontal diameter along that blue line, this what we call the 3 o'clock tangent. Up to what? So if sine is up to the circle, then what are we measuring up to what here? Up to so it's not the circle anymore, but it's intersection of the terminal side to that 3 o'clock tangent, okay? So here's how we're going to define this. The vertical distance above the horizontal diameter to the terminal side of the angle along the 3 o'clock tangent, also in radius lengths. So that's a mouthful. There's a lot there, but everything's important. Does the setup make sense? Okay, so it's still a vertical distance like sine is, but now it's not up to the circle, it's up to the terminal side where along the 3 o'clock, always along that 3 o'clock tangent. Okay, so let's investigate this a little bit. So here's a picture of it. So you see the angle is and the terminal side I'm showing in purple there, or pink, so we'll call it pink. And then depending on what the angle is, we get what we're saying is the length of that, the vertical distance above the horizontal diameter, up to the terminal side along the 3 o'clock tangent in radius lengths. So let's get this quantity here. So if this is r, so this can be any circle, okay? So just you can ignore the scale. So it's just any circle, radius r. Say it's in feet, okay? Could be 20 feet, could be half a foot, could be 88 feet, okay? It doesn't matter. All right, and then our blue line, 3 o'clock tangent, is L. So say we're going to measure that L in feet. So this new quantity that we're talking about would be not measuring that blue thing in feet. We have it in feet, L feet. But now we need it in radius lengths. So what computation would we do to write that blue line in radius lengths? Omar? No, sine is different. Sine is just up to the circle, right? So if we've got that length in feet, how do we calculate it in radius lengths?
Would you multiply the feet by sine? Would that make the difference?
That's to multiply it by sine. Christian?
Divide the length of L feet by R.
Divide L by R, and that'll get us how many radius lengths long that is. Isn't that right? Yeah. So this this quantity that we're talking about is L divided by R. Okay? L divided by R.
And that would be L in radius.
Exactly. This is right. So this is the vertical distance above the horizontal diameter still, but to the terminal side along the 3 o'clock tangent in radius lengths, or I'll say in radii. Right? Radii is synonymous with radius lengths. Okay, so now let's look at that. So L divided by R, it's this amount of height, right, divided by this amount of horizontal change, right? So it's vertical change divided by horizontal change. That's actually something else that you've learned a long time ago. Nothing to do with trig, right? Nothing to do with trig. When you take your amount of vertical change of a line divided by its amount of horizontal change, what is that? No, so not trig. 7th grade, 8th grade. Slope, right? Slope. So this, another way to talk about this quantity that we're talking about is the slope of what? Slope of what thing? The terminal side of the angle, right? So this quantity that we defined as vertical distance of a horizontal diameter measured in radius lengths is the same quantity as the slope of our terminal side, our pink line, right? The pink line, whatever the slope of that is the same as this quantity we defined before. So there's two ways to look at this function, its output. Okay, and so we call that, because it's this vertical distance along the horizontal, or along the 3 o'clock tangent line, the name of the function is tangent. Okay, so the output of tangent vertical distance above the horizontal diameter in radius lengths is also so just right here. Another way to talk about, so there's two ways to talk about the output of tangent. The slope of the terminal side, or the vertical distance along the 3 o'clock tangent measured in radius lengths up to the terminal side. Both of those are valid meanings because they're the same value, okay? They're the same value given an angle. Okay, so let's investigate this so we can come up with what are all the possible inputs and outputs of this, what we call the tangent function. So I can put that in now here. Okay, so this g of x is the tangent function. And so throughout class, I'll be talking about it both ways. I'll be talking about the tangent as the slope of the terminal side, and I'll also be talking about it as the length of that blue line measured in radius lengths, or measured in radii. Okay, so let's try to graph it here. So when that angle input is 0, what is the vertical distance in radius lengths along 3 o'clock tangent? Also, what is the slope? Oh, what's that? Distance is 0, right? And also the slope is 0 because that terminal side doesn't have any rise for whatever run you give it. So if theta is 0, tangent theta likewise is 0. So we can plot that point, okay? Get us started. Okay, so then what happens, let's go from 0 to pi over 4. So as we increase the angle theta, what happens to this quantity tangent theta? Alex wants it increases. Okay, right, so there's our positive values increasing. Okay, and so let's go to pi over 4, and let's analyze at pi over 4. That's the closest I can get to pi over 4 right there. What is the value of tangent and why? So now we're looking at pi over 4. Exit is the parade of latecomers. All right, so what is the, for pi over 4? Yeah. Why?
Because it's like how flops almost. If you flip it, it'll be the same on the other side.
Okay, so there's symmetry. You're talking about symmetry. Good. So if this is pi over 4, what's this angle up here? Same, pi over 4, which means, what about the radius and our height? They're the same. So if we're measuring that blue thing in radius lengths, how many radius lengths is that? It's 1, right? Because these are the same. And if these are the same, what's the slope of the pink line? 1, right? It's for the same amount of rise for run is 1. So when we reach pi over 4, which is about 3/4, we're at 1. So as the angle changes from 0 to pi over 4, tangent changes from what to what? 0 to 1. So as the angle changes from 0 to pi over 4, tangent changes from 0 to 1. Okay, what about from pi over 4 to pi over 2? So we're tracking the length of the blue line in radius lengths. What's happening? Does it increase or decrease? Starting at 1, it increases. All right, let me zoom out here, and let's. So I just want you to predict. Don't look at the scales because this circle isn't radius 1. But I just want you to, for this angle right here, predict about here. What is the value of tangent? Can you just make a prediction? What is the value of tangent? Is it -0.5? Is it 2? Is it 10? Is it 50? What would you just kind of predict for it? Nadine, can you make a prediction? What would you do? So what would you do to kind of predict the tangent of this particular angle that I'm showing you? What would you do? Take the radius length. Yeah, exactly. Count how many of these would be on the blue line. I think more than that. There's 1, right? Maybe something around 4, right? It's just something about 4. So maybe our tangent for this is 4, and therefore the slope of the pink line is, of the terminal side, 4, or whatever it would be. Okay, so we're here at 4, and I'm going to increase the angle some more. It's coming back. Don't be worried. Okay. So here we go. We had our 4. So I'm going to go increase the angle some more. What about now? Can't see it. And I'm going to go even closer to pi over 2. So I'll zoom out some more. So what happens as we get close to pi over 2? What happens to this quantity that we're investigating? Yeah, it increases. Like it just keeps increasing that I have to keep shrinking the circle to even see it. So here it's something like 20. So it'd be like something like 20 of these radius it would take to get up there. But I could increase it even more. So how big does it get? As we get close to pi over 2, how big does this quantity get? How long does that get? Yeah, basically, go ahead, Alex.
It does increase, but the amount that it increases has to increase because I don't think you can have it be parallel.
Okay. So you're talking about actually getting to pi over 2. If you get to pi over 2,
then it'd be parallel.
it'll be parallel. So you wouldn't. It's impossible, right? You can't measure that intersection because it never intersects. But before that, how big does it get? Patrick. So before we reach pi over 2, what's the limiting value, say, of this quantity, the blue line, the length of the blue line? Yeah, so you can imagine that, so you can really get any length possible just by getting close enough to pi over 2 and making that triangle tall enough and skinny enough, as tall as you want. Just by making that angle as close enough to pi over 2, you can get this tangent value, or this length along this, where the intersection point is, really as great as you desire. Okay? All it takes is getting that angle close enough to pi over 2. So what's happening? What's happening as we approach pi over 2? Yeah, and then what's that? We know what that is. So here's pi over 2 is about 1.57. Yeah, and you're knowing that for your test, right? What is that? Vertical asymptote, right? And we mentioned that at pi over 2, there's no intersection. So this tangent quantity doesn't exist because it never, that blue line just keeps going up and up and up forever and never, the terminal side never intersects it. Okay, so at pi over 2, tangent does not exist. All right, so let's see this in action here and get a good picture of it. All right, so we'll start from the beginning. This time we'll have the computer draw it for us. So one more time. As the angle increases, the angle of measure increases from 0 to pi over 2, tangent theta does what? What does it do? Come. So that quantity tangent theta, as theta increases from 0 to pi over 2, the quantity tangent theta does what? From what to what? So what is it here? What's the value of tangent right here at 0? 0. And it's going to, as we change the terminal side to measure pi over 2, tangent's going to increase to infinity. Watch it. Here we go. And so now when you get close, it's going to just take off. Okay, so that's what it looks like for angles from 0 to pi over 2, this tangent. It makes sense, right? That vertical distance starts at 0 and then takes off. Okay, so what's going to happen when we get to pi over 2? It doesn't exist. We get an asymptote. We're going to, as soon as we flip over into the second quadrant, what's going to happen? What's going to happen when that angle now goes greater than pi over 2? Why does it go to the other side? Okay, it's still going to be the 3 o'clock tangent. We're not going to move that tangent line.
There's going to be another asymptote at the other end. It's just that I'm not quite sure how the behavior will be.
Okay, so let's step back and talk and think about this quantity. What is the quantity again? It's the vertical distance along the 3 o'clock tangent in terms of its intersection with the terminal side. So here's the terminal side pointing up into the second quadrant. How is it going to intersect the 3 o'clock tangent? How or where?
Below the horizontal diameter.
So what? Can you be more specific? Why? What do you mean?
Because the tangent is going to be going down like this, so the slope is going to be negative.
Okay. So she's saying that we're pointing up to the second, but then if we kind of turned it around and looked the other way, that same line would be pointing down into the fourth quadrant, and that's where it would intersect a 3 o'clock tangent. So if we're measuring vertical distance above, then our result is going to be negative, just like sine, right? Just like sine. Let's see it happen here. Okay, ready? So here's our first. And then that being the case, So when I cross over here, I'm going to get a negative value for tangent because it's going to intersect below. Is it going to be a large negative value or a small negative value?
Really big thing.
What's that?
Really big thing.
Really big negative, right? Because just like here, we get a really big positive. As soon as we flip over, it's going to be close here to the y-axis, and it's going to take a long distance down on a blue line to intersect. So it's going to jump to a large negative right away. And here we see it coming up, right? We see it coming up. So in the second quadrant, is the value of tangent increasing or decreasing? Because the values are becoming less negative. You see that? So as that angle increases, we start with large negatives, and then we get smaller and smaller negatives. That's an increasing quantity. And what about when we reach pi? What's the value of tangent theta when we reach pi? 0, because we have 0 height. I'm not getting it exactly here. It's weird. Okay, I can't really get halfway. Anyway, so the closest I can get is about there. That's about the closest I can get. So we get to pi. Imagine, so this then has a slope of 0, or that vertical distance along the 3 o'clock tangent is 0. Third quadrant, so describe then third quadrant to me. Tim, what's going to happen now when my angle goes past pi and I'm in the third quadrant? So this quantity, tangent theta, what will it be? What's that? Okay, so make sure you do. How about, Pat, is that a hand?
Yeah.
Go ahead.
I was going to repeat the first process,
Why?
because like in the last one we just did, the angle could go through, and it's going to intersect it again, like the first time.
Right, so although the terminal side is pointing into the third quadrant, in order to intersect the 3 o'clock tangent, we're going to take the back side of it, and it's going to go back, and so he's saying it's going to repeat. So watch it, ready? So in the third quadrant, it just repeats what it did in the first quadrant. It starts at what value? And goes to? Positive infinity. And then, when we switch into the fourth quadrant, now the terminal side actually goes down there and intersects the way it's pointing. It'll go down there and intersect this negative value of tangent and repeat what it did in the second quadrant. Okay, so there's what we get when we do one rotation for the tangent angles. So let's talk about the domain and range. All possible inputs, all possible outputs for tangent. So I'll keep that on this page there. Let's see if we can do this at the same time. Okay, I think that's good. That's enough. So, what are all possible inputs? What's the input again? Measure swept counterclockwise. So what are all possible inputs that we could get? Yeah, Nadine. All real numbers. Hamid, do you agree? We can put any real number into tangent. Is that right?
Yeah.
Some people are saying no. Christian, why not?
Pi halves will not go in.
Yeah, look, remember pi halves. Tangent says, no, I don't know what to do with that because it's trying to measure the intersection of two parallel lines, or it's trying to measure an infinite slope, right? So pi over 2 doesn't work. Anything else not work?
All versions of pi halves multiples.
And also, bottom of the circle too, right?
Yeah.
So anytime that angle points straight up or straight down, or I'm sorry, not the angle, the terminal side. Anytime the terminal side points straight up or straight down, we get this undefined value. How many are there of those? All right, so we need a way to express all of them. Pi halves k. No, not quite, because then that would include pi, and pi's okay. Because pi halves k, if k were 2, then you get all the horizontal ones too, and those are okay because it's 0. So we need strictly the top. That's the right idea, right? So pi halves plus pi times k. So pi halves plus any multiple of pi times any multiple of pi. So starting at pi halves, we can go 1, 2, 3, 4, 5, 6, and that will get us all the top and bottom positions on the circle. Make sense? So all real numbers except these, pi over 2 plus pi k. What about all possible outputs of the tangent function? So look at the graph here. What are all possible outputs? What is our output again? It's the slope of the terminal side. What are all possible outputs? Let's see. Brian. He wants all real numbers. We can get every possible real number for a slope in the tangent. Yes or no?
Is infinity a number?
Well, he's just saying all real numbers. He's saying all real numbers. He's saying any negative value, any positive value is possible for the slope of the tangent, or slope of the terminal side. Look, in the first quadrant, we got from 0 to what? Every positive number we got in the first quadrant. And then in the second quadrant, we got every possible negative value from 0 down to negative infinity. So he's right. All real numbers are possible as outputs of tangent. You can get any slope. You can pick any slope. There's an angle that will give you that slope as its terminal side. Okay, so let's talk about the period. So good review for your exam. What is the meaning? So here's the first rotation of tangent from 0 to 2 pi. What's the meaning of the period? Who can give me, you got this on your quiz this week. So, Walter, period, what's the period?
How long a circle or something a circle will take?
It's not it, actually, and we're going to see why that's not it. So what was our definition of period? Buddha? That's right. It's the period is the interval of input. Let's write it one more time. Interval of input. Or say interval length. It's one value, right? It's one value. So it's an interval length of input values that gives a full cycle of output values. If you haven't learned it yet, learn it now. So, looking at our graph of tangent, what is the interval of input values, so the length, the interval length, that gives us the full cycle, or what interval length do we need before the output pattern starts over again? Jaden, what do you think? How far do we need to go? What interval length of input before the pattern starts over again? What's that? Pi. Why do you say that? Right? Okay. So he said pi because so you get all positives in the first quadrant, and then all negatives in the second. And then at pi, it starts over again. So you see, it's not necessarily a rotation. A period is not necessarily corresponding with rotation, because with tangent, you get 2 cycles in the first rotation. You get the full cycle in the top half of the circle, and then it starts over, and you get it again as you traverse the second half of the circle. Okay? So the period of tangent is pi. And you can see it from, say, like from here to here, from 0 to pi, you see how it starts over? Or you can take one continuous unbroken piece of this, say starting at pi over 2, and ending at 3 pi over 2. That's another way to see it. So right there, that's one piece from negative infinity to positive infinity. That's your full cycle of output values right there. Okay. What about the inverse tangent? So we spent a whole class on inverse cosine and sine on Thursday. So let's kind of just quickly just talk about inverse tangent. So in the inverse tangent, because you'll be doing that with your calculator. You'll be using inverse tangent with your calculator. So when you get an answer from your calculator, you got to know exactly what that number means. Okay? So if we talk about the inverse tangent function here, what would the input meaning be? What would the input meaning be? Jonathan?
The inverse?
Yep.
Maybe
Right. So it would be this. Yeah. And we also said another, don't forget, that what's our other meaning for this? Slope of the terminal side. Okay, so either this or the slope of the terminal side. It's the same value. So that will be the input into, so I'll write it there. So those are interchangeable, right? Either way. Okay, what are all possible slopes that we could put into the tangent? Jonathan, keep going. So what are all possible slopes? Is that all real numbers are possible as inputs into inverse tangent? Because we can get every slope out of tangent, right? We just saw that. We can get every possible slope from negative infinity to positive infinity. So in the inverse, that's the input now, we can input any slope that we want. That's right. What's the output going to mean then from arctangents? Joe? So what will the output be? So the slope of the terminal side is the input of arctangent. What will the output be? Did you start saying something? Or did you start saying something? Or no? I thought I heard you say something. No. Okay. So do you know what it will be? Don't know. Okay. Hamid? Measure of the angle, right? Just like inverse sine and cosine. What comes out? The measure of the angle. So we have the same issue. If we pick an input for, the input for inverse tangent would be like the y coordinate on tangent, right? So if we pick an input for inverse tangent, say this, 6.5, do we get one angle for every slope of 6.5? Or do we get more than one? More than one. So here's one. How many do we get? There's two. Keep increasing the angle. We'll just keep getting them, right? So what do we need? We need to, like sine and cosine, we need to take just a piece of this so that every slope from negative infinity to infinity maps to just one angle. Or every y-coordinate on this graph gives us just one resulting x-coordinate. So what are we going to do for that? What are we going to choose as our range or our angles to do that? What's the possibility? What could we do? Anna, any ideas? So what we need to do is we need to take a chunk of like some interval so that when we pick any slope or any y-coordinate of this graph, it'll give us just one x-coordinate. It's the same thing we did a week ago with inverse sine and inverse cosine. So I'm looking for some interval, say how about from 0 to pi? Or from 0 to 2 pi. Some interval that's for any y-coordinate that we pick, or any slope of the terminal side, we get just one angle out. Okay. Shola, any ideas? Anybody think they know? Nadine? 0 to pi. Will 0 to pi work? So if I pick, say, if I pick a slope, then in that range of angles, do I get just one angle in return? Boom. Just one. How about if I pick just 2? Do I get just one in return in that range? Yeah, right there. Okay, it works. 0 to pi would work. But there's kind of... Yeah, it's kind of, because it's broken up into 2 pieces, that's kind of not convenient. So can we do, is there not something else we can do? Christian?
Pi halves, 3 pi halves.
Pi halves to 3 pi halves. So from here to here.
Right, then you could get to those two values.
So from there to there. Do we get just one output angle, meaning x-coordinate, for any slope that we could pick? That would work. Yep, that would work. But again, if we put in the slope of 0, what would be the most kind of natural thing to get out for slope? Or for the angle? 0, right? So we'd really like a piece that has 0, 0. And if we put in, say 1, the most natural choice then would be, if I put 1 in, the most natural choice would be to get pi over 4 out. So really, this piece, for that, in terms of positive slopes, it's most natural to think about, we want these first quadrant angles. So then how can we do it? From what to what?
Negative pi halves to pi halves.
Yeah, let's do, so negative pi halves to pi halves. So we got the asymptote like this, and so we're talking about from here. And what about negative pi halves and pi halves? Include those or not? Are those possible outputs? No, right? Because they're not inputs of tangent, so they can't be outputs of inverse tangent because it's undefined. So this range from negative pi over 2 to pi over 2, the angle that you get out of inverse tangent is going to be, it's just like sine, except now you don't have the endpoints there. It's just like the output of inverse sine, the right half of the circle, right? The right half of the circle. From negative pi over 2 to pi over 2. That's what your output will be. So when you use your calculator in inverse tangent, you're going to get an angle between those two. And so if you're working in the second quadrant or the third quadrant, you have to make an adjustment, just like you did with those other problems, with inverse sine and inverse cosine. Okay, so that was a crash course in inverse tangent. So our possible, when you use your calculator, it's going to give you a number between negative pi over 2 and pi over 2, but not including those angles on the ends where the slope is undefined. So for instance, if we're here and I've got I've got this angle, I want to know this angle right here, and I'm going to tell you that the slope of the terminal side is negative 1/3. Okay, so the slope of the terminal side is negative 1/3, and I want to know what is this angle into the second quadrant. All right, so use your calculator and figure out what angle. Yes, ma'am.
I have a question about the output of arctan. When we're describing it, is it important for us to say that the output will only be within this range?
Yeah, your calculator, if you put, like for this angle right here, for negative 1/3, when you put that in to your calculator for arctangent, it's always going to give you the same result. And it's going to be within that range.
Okay, so when you're describing necessary, it's definitely have to include that.
Yeah, yes, definitely. So now I want you to find this angle measure in the second quadrant that gives a slope of negative 1/3. Can you do it? Gives a slope of a terminal side of negative 1/3. So we have slope and we want angle. What process is that? We have slope and we want angle. Inverse tangent, right? Arctan. Takes slope, or takes this vertical distance above the horizontal diameter along a 3 o'clock tangent, and we want angle. So you're going to do arctan, or tangent inverse. And when you put that in your calculator, what did you get? Negative 0.32. Or negative 0.32. All right, so first of all, does that make sense? Does that number, looking at the picture here, why does the number negative 0.32 make sense? 0.32 what? What is that talking about? Is that radius length? What kind of thing is that? Negative 0.32. What kind of number is that? What does it mean? I've only heard one person say it. What kind of number is that? Angle measure. This is angle measure. So the person, so you who said negative 0.32, is your calculator in radians? Or is it in degrees? It should be in radians. This is an angle measure, and that's a radians. Is this the answer to our question then? Because I asked for angle measure. No, right? What is negative 0.32 radians referring to in this picture? It's a clockwise angle from 3 o'clock, right? It's this angle is negative 0.32. Or about 1/3 of a radian, right? So 1/3, that looks about right? So about 1/3 of 1 radian clockwise. So how are we going to get the angle that we want? Alex, I want this angle. This angle took me to a slope of negative 1/3. I want that angle.
It was subtract 0.32 from I.
Right. You see that? So now this is also over here is an openness of 0.32 radians. So the angle would be pi minus 0.32. Question, Jaden?
Could you also add negative 0.32 to pi halves? Or
No, won't work. Because add positive pi, you mean? If you added positive, you'd end up somewhere up here. So 0.32 would be like this plus pi. So that's not the right angle. So if you're going to use arctangent, or tangent for that matter, in your calculator, you got to know what the numbers mean. You're going to get a number. You got to know what that number means so you can correctly answer the question you're asked. Okay? Does that example make sense? Any questions? Okay, so what is the point of, so I just gave you an example where I gave you the slope and asked you to find the angle. So it seems kind of not applicable. Like, when would you ever use that? So let's look at why tangent is important and useful in the real world, okay? So here I've got, so let's see. Okay, estimate the tangent right here. So what would you, if you were to estimate what the tangent was for this angle, what would you estimate the value of tangent to be? Morgan, could you give me an estimate for what the value of the tangent would be for this angle that I'm showing you right here? So what did tangent mean? So that output of tangent is measuring, what is it measuring? Right? Along the 3 o'clock tangent. So it's this measured in what? Radius lengths. So how many radius lengths is that blue line? About? Yeah, 0.7, 0.8, something like that, right? That's a good estimate for tangent of this. How many radius lengths that blue line is? About 7. And then also that's the slope of the pink line. Okay? So how could I, on the same diagram, how could I represent with other lengths? I want to put line segments on this diagram to represent sine and cosine. How could I add other line segments to represent sine and cosine? Jaden.
You could do for cosine, you could do the vertical distance above the horizontal diameter to the circle radius length.
For which one? Sine or cosine?
Cosine.
Vertical distance above the horizontal diameter.
Sine.
Sine, okay? All right, and what about cosine? Right. So like this? So couldn't we do this, right? So again, so you got to ignore the scale here, right? Ignore the numbers that you see on the scale. If this is the length of this in radius lengths is cosine, and the length of this in radius length is sine. So estimate cosine right now. What would you estimate the cosine to be? Justin, what would you estimate the value of cosine to be? 0.65. No, so you're just picking up the scale. What is cosine measured in? Cosine's measured in radius lengths. So it's not 0.65 radius lengths. What was it more like? 0.2, 0.4, 0.6, 0.8, 1. So here's your radius length, right?
Yes.
So what would you estimate cosine to be?
1.7.
Yeah, even more, right? 0.8, 0.85, something like that, right? So yeah, so it's about 80 to 90% of a radius length. What about sine? Malin, what would you estimate the value of the sine to be? Point 0.4? Yeah, 0.4, 0.5, about 4/10 of the way up the radius, right? Okay, so, and what did we say tangent was? Tangent is, if this is our radius, and this is L, then we said tangent theta was what? L over R, right? Measuring that blue line in radius lengths, L over R. And we said it was about 0.8 or something like that. But then Tuesday, you talked about the sides of this triangle that's formed, right? What side is this right here in this right triangle? Relative to this angle, what's that side called? Opposite. And relative to this angle, what's this leg called? Adjacent, okay? So look, tangent theta is L over R. But by similar triangles, it's also what? What other ratio can we form that has the same value as L over R in this picture? You see that those are just similar triangles. So that ratio of L to R is going to be the same as the ratio of opposite to adjacent in that triangle. So there's a third. I think you came up with, on Tuesday, you came up with the ratios for sine and cosine. And sine you came up with? Because the hypotenuse is our radius, right? So if we want the length of this right here in radius lengths, that's sine, how would you get that length right there in radius lengths? You would take it and divide by the radius. And that would give you the vertical height and radius lengths. That's what sine is, right? And if you wanted the length of that black bar in radius lengths, you would take its length and divide it by the radius. So now you have a third tangent then is opposite over adjacent because it has that same ratio. Opposite over adjacent has the same ratio as that length to the radius. Okay, so these allow you, did you solve some right triangle problems then on Tuesday? Did you do that? So now you have another tool for doing those kinds of problems, tangent. Okay, tangent is opposite over adjacent. Any questions before we do some examples? Okay. So here's an example. So this is totally realistic. You're going to find the height of a tree, so you can use this instrument here that will measure the angle, what's called the angle of elevation. The angle of elevation is the angle swept up from horizontal. So this is the angle of elevation from this level right here, swept up to the line of sight to the top of the tree. 39 degrees. And then the distance of that instrument from the tree is 70 feet. Okay, and we want to know the height of the tree. What's the height of the tree, which is shown over here, right like this. Okay, so we need to have if we're going to use what we call triangle trig, we first need a right triangle. So we need to superimpose a right triangle into the situation. It's going to help us solve for the height of the tree. So can you get an image of what triangle would be helpful, what right triangle would be helpful? Here. So, Jared Smith, can you describe the right triangle that we're going to use to help us get the height of the tree? All right, so how about, is the instrument part of your triangle?
Yes.
All right, so tell me the first side starting at the instrument.
Going horizontally from the vertex of the instrument to the tree.
All right, he wants a horizontal line from there to there. Okay, one side. Next side.
The terminal side of the device going up to the top of the tree.
Oh, the blue line that's already there. Okay, so we got this horizontal line. We got this blue line that's already there. And finally, straight up and down the tree. Something like this. Okay, so we've got this triangle. It's a right triangle. And then we got to identify what we know and what we need to find. So in this triangle, what's one thing that we know? Fuda. You know the angle. So this is our angle in question. So when we use those, when we use the ratios, and we're talking about the tangent of an angle, or the sine of an angle, or the cosine of an angle, that's going to be the angle in question. Okay, so this is going to be the angle that defines our opposite, adjacent, and hypotenuse. What else do we know? Keep going. She's saying this right here is the adjacent side down here. Is this the adjacent side? And she's saying it's 70 feet. Okay, Joe, tell me something else. What's that? What do we do next? Vertical line. What about the vertical line? Is the tangent. Is it hypotenuse, adjacent, or opposite? It's the opposite side. Do we know what it is? Is it going to help us? Yeah, this is going to be one step away from getting the height of the tree. Taz wants to jump in. I think, right? Is that a hand? Yeah.
Well, we know if we take sine of 39, it would be the height of that opposite side of radius length.
Okay.
And then if you multiply that by the radius, it gives you how many feet it is, and then you just add that.
Okay, do we know the radius?
Oh, no, you would.
Yeah, the radius is going to be longer than 70. But no, I really like that because he recognized that this right here, the sine of 39, is going to be that side in radius lengths. That's really good. That's really good that he saw that. The problem is that the radius, we don't have the radius, which is in fact the hypotenuse. And so we have the adjacent. We want the opposite. So which of the ones bring those together? Brian. So we have adjacent, we want opposite of 39 degrees, so we need, is it going to be sine, cosine, or tangent? Tangent. So tangent of 39 degrees is going to equal x over 70. So let's just start by finding the tangent of 39 degrees and seeing if that number makes sense in the situation, okay? Find the tangent of 39 degrees. So we're calling the opposite side x, that's fine. What is the tangent of 39 degrees? And let's use our knowledge of tangent just to kind of do a mental check. What do you get? 0.81. How can we make sense of that number? So 0.81, does it make sense? Omar? If it's the tangent, what does it mean?
It kind of does make sense. It's almost, if you look at it in radius.
What in radius lengths?
I mean, like, not radius, sorry. The adjacent. We put it like as an example.
Yeah, but our output of tangent didn't really have to do with this adjacent, right? What did it have to do with?
Oh, okay. I see what you mean.
So what is 0.81? What's the output of tangent? What's the meaning? Brooke, do you remember the meaning of the output of tangent? Okay, that's true. But the problem with that, using that meaning, is our circle would come out like this, and then we would have this distance. Kind of hard to see, so maybe the other meaning would be better. What's the other meaning for tangent? Slope. All right, so slope is rise over run. So does that seem like 0.81, meaning the rise is about 0.8 of the run? Is that reasonable? Seems like it's in the ballpark, right? This triangle looks like the rise and the run are about the same, okay? And so that's what this is saying. This is the rise is a little bit less than the run. Okay, now we want to get this x value, so we can solve this equation. X equals what? 70 times tan 39. What'd you get, Walter? No, what will x be? What will the units of x be when we do this? X is the opposite side, right? So 56 point what? 7 what? 56.7? 8? Okay, is it radians, Celsius, inches? 56.8 what? Feet, because it's the length of the opposite side. And is that the height of the tree? How will we get the height of the tree? Shola. What value is that? So the height of the tree is going to be 56.8. You're looking at this right here? 3.5 feet. 60.3? Height of the tree. Any questions? Yeah, Alex.
It's more like a common thing.
Sure.
Back in high school, me and a group of friends, we launched weather balloons.
Okay.
They went up pretty high, so high that we couldn't really, we didn't have any devices that could track the altitude.
Yeah.
So pretty much what we did is we had a camera, I set it at an angle, we took pictures, we had a reference point, and with pretty much that we figured out something like the estimated the altitude.
Yeah, this is totally useful stuff, right? So this, exactly. There's lots of examples of how you can. So here's another cool example like that. Well, first of all, just this is kind of a sticking point. So these terms often come up in these examples: angle of elevation, angle of depression. Although normally you don't see them both in the same problem, but we'll just talk about them both at the same time. Angle of elevation is what we just saw for that angle up to the top of the tree. It's the angle swept from horizontal. Swept up from horizontal is your angle of elevation. Okay? This is angle of elevation. Angle of depression is similarly the angle swept down from horizontal. This one's trickier. Okay? The angle of depression is the angle swept down from horizontal. Why is it trickier? Because oftentimes students will make a triangle like this. The problem will say the angle of depression is 42 degrees. And what will they do? Students will make that angle right there 42. That's not the angle of depression. The angle of depression is the one that's swept down from horizontal. So this is not the angle of depression. Okay? Now you could use the angle of depression to find that angle. It'd be what? 90 minus 42. Okay? If that angle was given, the angle of depression was given as 42, then that angle would be 90 minus 42. And this would be your 42 up here. Okay, so just as an example of that. So this is saying that the rope's angle of depression is 53 degrees. So what is 53 degrees in this picture? Okay? So what angle is 53 degrees in this picture? Shola. What angle is 53 degrees in this picture? Right. It's this one here, swept down from, that's your 53 degrees. So again, the pitfall here, students will, okay, here's my triangle, right, like this, and then oh, there's 53 degrees. Wrong, okay? So what is that angle? It'd be 90 minus 53. Okay, so here's another cool application. So it's similar to the height of the tree, but now we don't want to, we're far away from the top of this thing, so we can get a good line of sight to the top. So we don't want to measure our distance from, we don't know what it is, right? So this is in the middle of the mountain. We don't know what that distance is straight below the tip, okay, of the top of the mountain, the peak. So instead, what they can do is they can take one measurement, get the angle, and then go a distance, and take another measurement, another angle, and so this is the information that we have. So the question is, how tall then is the Matterhorn? So what are we going to do? We're going to have a homework problem like this over the weekend, so we better have a strategy to do this. Any ideas? Alex?
I have a question. Do you have to use both triangles? Or
Do you have to use what?
do you have two lines of sight? So which one would you pick to use, or do you have to use both?
But what I'm saying is, if you only have one triangle, you could get that angle, but you don't know any lengths of any sides. You can't get this one because it's in the middle of the mountain.
Oh, okay.
This is what you're trying to find, and you certainly don't know what that is.
All right.
So this is a technique that they use by getting two angles and their distance between them. We can do a series of steps using our right triangles to get that. Christian?
I think you could use the first angle, 30 and 150 feet, to get your hypotenuse.
So that's 1,500. So let's call this capital H. So, and then we're going to need to call this something, right? Let's call that X. So we're going to use tangent, so at 30 degrees. So we're going to use tangent, sine, or cosine? Cosine. We know what this length is here? This is the hypotenuse. We've got opposite and adjacent.
Probably want to get the hypotenuse first.
No, we want to find the height of the mountain. We want to find the height of the mountain.
Wouldn't that help you find that?
In a roundabout way. So we have information about the adjacent. We want to know the opposite. So what brings together adjacent and opposite? Tangent. Tangent of 30 would equal what? Opposite over, well, now what's the adjacent? So this is 1,500 from here to here, and we're calling this X. So this would be, the adjacent would be 1,500 plus X. So we've got two unknowns. And then in the second triangle, tangent of 35 would equal, so now this smaller triangle, what would it equal? H over X. So there's your setup. You got two equations, two variables. You can get the value of H. Does it make sense? Okay, don't forget your exam. Use the tutor center. If you want to go now to the tutor center for the last minute questions. It'll be normal homework for Tuesday. Check Blackboard. Have a safe weekend. Oh, it's fine. I mean, you got through what we planned, so that's fine. How did it go? Did it go okay? No one was expecting amazing. But they gave you due respect. Yeah, no problem. Good.
About as attentive as they are for you, so.
What's that?
I said about as attentive as they
Oh,
are for you,
that's-
so.
yeah.
That's exactly.
Good. Excellent. And then for let's see.
Last time, they were pretty good about asking questions about because they could remember rational functions.
Oh, cool. All right, that's good. You could just do. Let's see. So, what was the homework for today? Was there?
There was a homework.
All
Unless
right.
there was what we're
Just
doing.
you're getting the quiz, right?
Yeah, I gave them quiz last week, and I have it this
Yeah.
week.
Okay. And so then, from there, I would. You might just field any last-minute questions about the exam, but don't spend long. And then you could do more odd problems from
For this
Module 8.
homework.
just more practice of the. You could finish this problem if you wanted to.
I'm sure they'd want to. So.
Yeah, finish that one. And then, which is just algebra. Hopefully they can do that. Should be able to do that. Use substitution, you know.
Yeah.
Yeah, it's not hard. And then any other odd problems at the beginning of Module 8? Any applications?
Okay.
Be fine. Thanks, you too.